Okay, so let's begin. Good morning. Now, today I would like to do named entities and multiwords, which have been very vexing problems for natural language processing. Okay, for a long time, natural language processing did not take these problems very seriously. Okay, the field was concerned with semantics, syntax, and so on. But there were very complex problems, okay, which was not appreciated very much at the level of words, and these are named entities and multiwords. So, these are pretty lower level problems, that means at the lower layer of natural language processing. Therefore, they are very suitable for application of machine learning techniques. So, what I would like to first do is that we have a recap of what we did in the last class. So, in the last class was mainly on statistical machine translation, and the most important concept covered in that class was word alignment with expectation maximization, where we found that the vocabulary mapping probability can be found in terms of the sentence alignment probability and vice versa. Okay. So, there was an EM based algorithm that was the most important point covered in the last lecture. And we also mentioned that phrase based statistical machine translation is the ruling paradigm now for machine translation. But many language pairs, machine translation is an activity involving two languages. So, many language pairs need additional machinery, okay, like tree alignment, factors, and so on. But the foundation for everything is really word alignment. Okay. Everything begins with word alignment, and statistical machine translation discovered a way of modeling word alignment. So, this was the most important point covered in the last class. Now, named entity and multiword processing, they belong to the first three layers of processing really. Okay. We have to make use of part of speech tagging, we have to make use of grouping of words, and that is needed for named entity and multiword processing. And these days there is a lot of application of deep learning, use of word vectors for named entities and multiword processing. So, we will cover that in the last lecture on deep learning and word vectors. And again, multiple languages need to be considered, because many languages attach a suffix to the named entity, to the proper noun. Okay. This does not happen in English, but many languages transform the named entity depending on the case marker after this or the postposition after this. Many languages also transform the words inside a multiword, inside a word combination. Okay. So, we have 2-3 words combination. Morphological processing goes deep into the word. Okay. This goes to the first word, second word, and so on. Therefore, the property of the language plays an important role in multiword processing, and of course, we need strong algorithms to do this processing. Okay. So, named entities and multiwords need special attention. In cross-lingual search, named entities need transliteration and not translation. Okay. So, when we make cross-lingual search, the query is in one language, the retrieval is in another language. So, this example is interesting, and Hindi speakers would appreciate this. Pooja ne puja ke liye phool toda. Puja and puja. So, this first puja is a proper noun, and second puja is worshipping. Okay. So, we need to translate this puja into worshipping, and this puja should be transliterated. Okay. So, this detection is needed. Given the same sentence, we have to identify which entity needs transliteration, which entity needs translation. Similarly, for an entity like Indira Gandhi Open University, so this is the name of a person, okay, one of the prime ministers of India. Open University is a part of this name. Open and university get translated, okay, Mukt Vishwavidyalaya, but Indira Gandhi, the name, does not get translated. Okay. So, when we translate this group of words, we need special attention in transforming a part of the whole group differently. So, all languages have this kind of problems, and adverbial multiwords in French are particularly difficult to process. Of course, many of them follow particular patterns, and therefore, regular expressions can be constructed here. But translating them word by word would fail. Okay. So, if we give our attention only to particular words more than part of speech tagging and begin to process them word by word, then the processing will really fail. So, we will talk about that little later, but adverbial multiwords are important concerns in French. Text, of course, definitely contains lots of multiwords. Okay. Many important political documents, economic documents have named entities which need to be processed, and many times named entities consist of more than one part. So, this is an example of a name, this is an example of location, this is an example of again name, and they need to be identified. So, in multiwords, we need to process the constituents together, and in this kind of processing, named entities and multiwords, we find that features play a very important role. Okay. So, we know that in machine learning, features are important, and modeling of these features have to be given special attention. Now, here we find that entropy based approaches have been effective. Okay. The modeling is based on entropies, and the maximum likelihood based modeling has not found it very natural to incorporate features. Okay. So, this is an important point of view which we need to keep in mind for empirical natural language processing. Okay. So, modeling of features is very important, and maximum likelihood of data or observation does not seem very natural. So, let us get into some foundational insights. Why features? We said that empirical natural language processing begins with this kind of argmax formulation. Okay. So, if you want to get the best possible A from B through the noisy channel formulation, then A best is argmax of A, probability of A given B. This is the start of any statistical modeling, and many speech and NLP problems fall in this framework. So, from the part of speech tagging discussion, we understood that this essentially is a matching problem. Okay. We break A and B into small parts and try to match. Okay. In part of speech tagging, for example, we get the part of speech tag sequence, break it into small parts like bigrams, for example, and here this is the lexical probability or an emission probability. This is also broken into small parts, and then we reconstruct a hypothesis. We construct a hypothesis and try to find it in the hypothesis space. Okay. This is the fundamental point. So, when we decode, we try to find out parts of A and B in the hypothesis space matching with parts in the data. And this kind of matching is either by parts, okay, which is the generative approach. Hidden Markov model is an algorithm making use of this philosophy, and the other approach is matching by features, okay, which is the discriminative approach. And examples of this philosophy are maximum entropy Markov model and conditional random field. Okay. So, this is a very foundational point, and whole of statistical natural language processing can be said to be concerned with breaking A and B into small parts, matching them and finding the one with highest probability. Okay. So, the matching is either on parts or on properties, which are features. Okay. So, this point is very important to keep in mind, because so many problems need this understanding. So, if this point is clear, let us get into a bit of mathematics, and we would like to look at the foundation of maximum entropy Markov models. Okay. What we did before was hidden Markov model in the context of part of speech tagging, which was a generative approach. So, today we will spend a little time on maximum entropy Markov model to understand how features are incorporated in the theory, and then see what to do about multiwords and named entities. Any question at this point? Any question on the foundation here? Yeah.
In the second part of the formula, why would you divide with P of B?
Because you see, it is argmax over A.
So we have not
So, and since we are interested only in relative scores, okay, PB is constant everywhere. That does not affect the ranking. Yeah. Anything else? No. Okay. So, matching by parts, matching by features. I am sorry, there is a spelling mistake. I will correct it. Okay. So, maximum entropy Markov model. We would like to derive the maximum entropy Markov model from fundamental principles. So, suppose we have these observations x, x1, x2, x3 up to xn. These are the observations, and the objective to be maximized, which is the entropy, is sigma I equal to 1 to n pi log pi. This should be log, okay. Log pi, log to the base 2. And pi is the shorthand for probability of xi. There are two constraints. One is that sigma pi I equal to 1 to n must be equal to 1, and there is another constraint which brings features into modeling. Okay. This brings the features into modeling. So, this expression sigma I equal to 1 to n pi fj xi is equal to kj is a constant. Okay. This is expressing the constraint that the expectation of the jth feature of xi is a constant. There are m such features. In fact, we will see later that the constraint mandates equality of model expectation with data expectation. Okay. So, so this is how the feature is brought in. This is how the data is brought in. Okay. We will see that little later, and I hope you can see that these two constraints are okay. The first one is of course a well understood constraint, because it is saying something about the probabilities. PIs form a probability distribution. So, this is for discrete probability distribution. And the left hand side is indeed the expectation of the features, expected value of the features. Okay. So, each observation has associated with it m features. To make this more concrete, let us take this example. Example to clarify the second constraint. Suppose we are doing part of speech tagging. Okay. The part of speech tag on each word is a random variable with n possible values. Okay. X1 can be equal to nn, noun tag. X2 can be VB, the verb in base form. X3 can be JJ, adjective, and so on and so forth. Okay. So, these part of speech tags are obtained from the pen tree bank. Okay. So, these are nothing but labels which sit on every word. Now, in hidden Markov model based part of speech tagging or the generative model, we have seen that there are two parameters. One parameter is transition probability. What is the probability that a verb follows a noun? What is the probability that a noun follows an adjective? This was one part of the parameter space. Another parameter was what is the probability that the tag noun generates apple? Okay, what is the probability that VB generates play? Probability that JJ generates red. Okay, so that's the emission probability, and the transition probability is probability of tag to tag transition. In that modeling, there was no role of features. Okay, why features? We'll see just now. So the probabilities are for these n tags, p sigma pi I equal to 1 to n, pi equal to 1, and p1 can be probability of nn, p2 can be probability of VB, p3 can be probability of JJ, and so on. For each word, we have these labels and their probabilities. So now we say that for each xi, there are m features. We previously decide what these features are. For example, does the word end in shun? Okay. Does the word have at the end a suffix tion? We know that if this feature is correct, if this feature is true, then the word must be a noun. Okay. Like for example, the word promotion, which is a noun, locomotion a noun, transportation a noun. So any word ending in tion must be a noun. Okay. And that's a very important piece of knowledge. Okay. If the modeling does not make use of this information, then it is losing something important. Okay. In the generative model, which is based on hidden Markov models, we do not have a way of dealing with these kind of features in a very natural way. Okay. But we could take care of these if we made use of features. So we will introduce features in the modeling as was shown in the last slide. Okay. We will introduce this kind of features. Does the word have shun at the end, and so on, and work with the expectation of these features, expected value of these features. Okay. And the guiding principle will be that the model expectation of features should be same as the data expectation of the feature. The second part we will see very soon. Okay. So is it clear why we bring in features and why we need special modeling for features? Okay. Any question? Okay. So now the expression which we need to maximize is the entropy, of course, subject to the constraint that there is a probability distribution, and the constraint that the features, expected value of features, have to be constants. Okay, expected value of the features. So we introduce Lagrange multipliers, lambda for first constraint, which is a single constraint, and mu j's for each feature. Okay, for each feature there is a constraint. This expected value must be equal to kj, and each is multiplied by a Lagrangian multiplier. Okay. So, this is the expression which is in the dual space to be maximized. Okay. After that, of course, the steps are very routine. We take derivative of f with respect to pi. We are interested in the values of pi. So, delta f delta pi would give me minus log pi, it is not really ln, log pi minus 1 plus lambda plus j equal to 1 to m mu j f j xi, and that should be equated to 0. We are maximizing this expression. Okay. Then we get ln pi is equal to lambda minus 1 plus this expression j equal to 1 to m mu j f j xi, equating it to 0. Okay. Now, therefore, pi becomes e to the power lambda minus 1 and e to the power this quantity. Okay. And we can always transit from log 2 space to ln space by a constant. So, e to the power lambda minus 1 into j equal to 1 to m e to the power mu j f j xi. So, this sigma becomes multiplications. Now, if we let e to the power lambda minus 1 equal to a, some constant, and e to the power lambda j equal to a gamma j, which is again a constant, then pi equal to a into j equal to 1 to m gamma j to the power f j xi. This should be xi. Okay. And the normalization will yield a equal to this quantity. Okay. How will this come? Because if I take sigma pi, okay, and sum this up, then the left hand side has to be equal to 1.
Are you sure it's not mu j, or there is simply discrepancy between the two lines?
Oh, this is mu j.
Yeah.
Mu j, I'm sorry. Yeah, I have to make this change. This should be mu j. Okay. Tau j. So, yeah, I'll make these changes. Sorry. So, this will be the expression for the constant, and the final probability expression will be in this form. Pi will be an exponential involving the features and their weights divided by a normalizer, or in this form, this should be I am sorry. Okay. So, this will be the final probability expression. Okay. And we many times see in maximum entropy or conditional random field based papers that the probability is shown to be an exponential. Okay. How does the exponential expression comes? It comes because of maximizing the entropy, okay, and equating the features expected value to be a constant. Okay. So, let us look at this expression. The probability of each random variable's value is expressed in terms of the features and their weights raised to the power e, okay, and divided by a normalizing constant. So, features are already given. Features are things like, does it have a particular suffix, okay, does the word have a particular suffix or not, and we have to get their weights. Okay. So, these weights are to be found from the training data. For example, the weight of Sean feature will be high for PNN and low for PVB as dictated by the training data.
What about the interdependence or independence of the features? Of the distributions of the features. What about that?
Yeah. So
Motion cannot be with a noun. They are correlated, as far as I can tell.
yeah.
What about the probability distribution? It might be different. So what is known about that? Whether all these holds, and
Yeah.
for this to hold, you need the independency assumption.
Yes.
How far is it true?
This is surely this is not very true. Okay, surely this is not very true. We make it because of this product. This, for example, one sec. Okay, here itself there is an independence assumption that the features are independent of each other. No, so surely this is not completely true, but it is an engineering.
It doesn't mean anything to be completely true. Or if you are not in fuzzy logic,
Yeah.
it means nothing. Either it is true or it is false.
No.
So if it is degree, then you should say that it approximates some probability distributions within a certain error margin. That would be correct. And my question is, what is known about that in the field?
No, features are assumed to be independent of each other.
Yeah,
Yeah.
nobody just took the pain to test how far they are independent of, because correlated variables do exist in statistics, right? The basics of abduction.
Yeah.
So people just simply don't care about that. They just play with those symbols and question as if it would be true, knowing full well it is not true.
Yeah.
I don't see why we I don't see when we assume that the features are independent. Are we assuming something about the independence here?
Yeah, the features are assumed not to affect each other.
No, this is just the expectation of features, right?
Right. Yeah.
And the different features have different expectations. That's all these equations tell us. It doesn't say that one is independent of the other.
No, there is, because you see this probability of xi,
Yeah.
okay, the probability of xi, and for each I you have each xi there are a set of features. There are a set of m features, okay, and the interaction of these features is not captured here,
Yeah, it's
right?
captured.
Not captured here, yes. So, so I'm not sure that this modeling is completely. So this fj, for example, okay, if fj is not a function of only xi, it is a function of fk, fl, and so on also.
Yeah.
Okay, that is the point. So you are right that this does not violate the formula for expectation. That's right. But this function is not completely accurate.
Yeah. Okay. So my point is it doesn't assume independence assumption, but meanwhile it doesn't modelize the dependence, right? It doesn't modelize dependency, but it doesn't assume independence assumption either.
Yeah. So, so the independence of features is, or the dependence of features is not coming into picture in the modeling, is what was the objection that Professor Boite was raising. And if we could introduce other features, which would become a very complex function, I think, here. Okay, then probably there is a way of modeling. Probably. Yeah. So, so the point is that whenever we maximize entropy, we do get a formula for the probabilities in an exponential form. Okay, so that is the important point, and the exponential form comes with features whose weights are μj's. Okay, and they need to be obtained from the training data. So, as dictated by the training data. To bring on the data in the whole picture, we insist that the expectation of features as given by the model is equal to expectation of the features as given by the data. Okay. So, this is a constraint which is introduced to create a training algorithm. Okay. And the training algorithm is called the generalized iterative scaling, okay, which is an iterative algorithm which progressively changes the weightages of the features, okay, changes the weightage of the feature, and finally, when the algorithm converges, we get a set of weight values for each feature. And we find that for nouns, indeed the feature for shun becomes high, for verbs those features become low, and so on and so forth. That is ensured by the expectation of the data and expectation of the model being equal. Okay. So, I am not going to describe the generalized iterative scaling, okay, because it is very similar to an incremental improvement, okay, over a set of values, just like in expectation maximization or gradient descent. Okay. So, if time permits, we will describe this, but the most important point is that there is an exponential form for the probabilities which depend on the features and their weightages, and we would like to make use of this in our problem solving. Okay. So, then we move to the study of multiwords expression. Yeah.
Can I ask a question about maximum entropy?
Yeah.
So here we train a model
Hmm.
where we want to maximize the entropy to have a good like sequence labeling system.
Correct. Yes.
But in the meantime, for instance, last course,
Hmm.
when we were doing some word alignment, we were minimizing the entropy of the alignments. You have shown some curve, and after each iteration of the EM algorithm, we were minimizing the entropy. And this is also the same thing when we train a language model.
Hmm.
We try to minimize the perplexity, which is something like homogeneous to the entropy.
Right.
So sometimes we minimize entropy and sometimes we maximize it. So
Hmm.
how do we know if we need to maximize it or to minimize it?
Okay.
That's the problem.
Good point. Okay. So, yeah, let us get some basic points. Yeah. So, in maximum entropy based approach, the whole point is that we would like to get values for these probabilities. Okay. We have to make an estimate of these probabilities. Okay. We have no idea about the form of the probability distribution. We do not know whether it is binomial or Gaussian or Bernoulli, Dirichlet, whatever. We do not know. We have no idea. But we just know that there is a probability distribution which must satisfy this constraint, and because the probability distribution is given, we can think entropy. Okay, and entropy is given. Now, since there is no other information available in the world, the uncertainty is maximum. Okay. So, one way to find out these probability values will be to maximize the entropy. Okay. For example, if you try to maximize the entropy of the probability distribution for tossing of a coin, we will find that the maximization of entropy leads to head probability being half, tail probability being half. It will lead to that. Okay. This is well founded. Okay. Maximum entropy principle says that in absence of any other information, the best thing you can do is to maximize the entropy, okay, because there is no other information. Now, does it contradict our last class where we tried to minimize the entropy? Does it contradict that? Okay. So, So, your question is actually this, that maybe maximize likelihood, is it equivalent to minimize entropy or maximize entropy? This is the question really. Or what is the relationship between the aim of maximizing the data likelihood and minimizing or maximizing the entropy? What is the relationship between them? That is the question. So, in the last class, when we introduced entropy, okay, what we tried to do was to see that when we get the when we want to get the probabilities of word alignments, okay, probabilities of dictionary mappings, do we get to a stage where the uncertainty is maximum or minimum? Okay. In such a case, we would like to get minimum uncertainty. Okay. We want to understand that the let's say the French translation of day is what? Jour. So, we would like to see that this probability value becomes the winner probability after the algorithm terminates. Okay. And when we want to do that, we would like to make the probability distribution very certain. Okay. And we want to make when we want to make this probability distribution very certain, then the entropy should reduce. Okay, reduce. Now, maximum data likelihood will lead to this situation. Okay. Whereas, if we do not have any other information and we start with the goal of finding a probability distribution from nothing, okay, then we cannot do anything other than maximizing the entropy of the probability distribution. Okay. That is because we do not have with us the maximum the data likelihood expression. Okay. So, then I think your question will be that if we had done the same thing for alignment and dictionary probabilities, okay, then are we coming to a contradictory situation that we have to maximize the entropy? So, let me think about this question, okay, and let me come back to that. Yeah. So, is there a contradiction in the philosophy? Yeah. So, the point you see is that you would like to make the probability distribution very definite, okay. So, which really is reduction of entropy, but does it contradict this principle? We will see that. Okay. So, multiword phenomenon is really a very very serious problem, okay, which was understood maybe 10 years back or so. First of all, we can have long expressions with variable relationships. So, if we have a expression like this: colon cancer tumor suppressor protein, okay, it is a protein which suppresses the tumor of colon cancer. So, here the head is protein, and we have a modifier relationship between protein and suppressor, protein causing suppression. And there is a modifier relationship between suppressor and tumor, suppressor causing tumor or suppressor suppressing of tumor, and the tumor in cancer, tumor caused by cancer, cancer of and colon, cancer of colon. So, between every two words we have a different kind of relation, sometimes same, sometimes different relation. Okay. So, in this whole structure of multiple words, there are many different kinds of semantic relations. Okay. So, this gives rise to a difficulty of processing for multiwords. Multiwords also have an idiosyncratic behavior. So, put the sweater on, this on does not require any argument. Put the sweater on what? That is not required. That question need not be answered. Put the sweater on means to wear the sweater. Put the sweater on the table, this has a completely different meaning from the previous case. And put the light on, that means light on, switch on the light, this has a different meaning. So, the structure put and on has idiosyncratic behavior. Okay. It is first of all polysemous, and it also has idiosyncratic behavior.
Actually, the second case is not a multi-word expression.
Put the light on
On the table.
In the second case is not a multi-word expression. Yes.
But in the two other, yes.
Yes. Yeah. So,
Is the verb with the particle.
right. So, you have to detect this as a phrasal verb, this as a phrasal verb, this as verb and preposition combination. Okay. So, whether this preposition is a part of a phrasal verb or is it a part of the preposition phrase is the basic question. Okay. And this is very characteristic of multi-word expression. Also, put on when it is a phrasal verb is ambiguous. One meaning is to wear, the other meaning is to switch on. So, these are idiosyncratic interpretations that cross word boundaries or spaces. Now, of course, machine translation is very much concerned with multi-words. In the first class, we saw some examples of completely wrong translation if the multi-words are not processed properly. This was shown, and this is very recent. Google is still doing this kind of mistakes. Does information retrieval need to worry about multi-words? Yes. For example, if you give a query of this kind, red herring in Red Sea, this is a completely nonsense query, okay? Because Red Sea is the name of a sea, of course. Red herring is not a herring at all. Okay? Red herring means something irrelevant, okay? Deliberately used to divert the attention. Okay? So, suppose we are debating on some issue and I bring in completely orthogonal point just to divert the whole point to my advantage, that is called red herring. Okay? So, in political debates this often happens. So, this query really does not mean anything. So, red herring, any diversion intended to distract attention from the main issue. And Red Sea has one sense, a long arm of the Indian Ocean between Northeast Africa and Arabia. So, this particular query does not have anything, and fortunately the search engines are able to detect this. So, what it produces as result is the meaning of red herring from the Urban Dictionary. Then a sea of red herrings is behind opposition to EPS proposal, etc., etc. So, it does not try to look for documents which has this combination, because it does not have. Part of speech tagging also has to be concerned with multi-words. This is a very dramatic example which the Hindi speakers will appreciate. I will just say this, okay. So, even though others may not appreciate, NLP बहुत कठिन विषय है, भाग लो या भाग लो. Okay. So, this means the following. NLP is a hard subject, take part or stay apart. Okay. So, the same word combination भाग लो या भाग लो, same word combination, okay, is meaning this is having this meaning. So, you have to process भाग लो appropriately from the context, which is a very difficult proposition. So, भाग लो is an ambiguous combination. Then wordnet and sense marking also needs to be concerned. So, for example, if we are doing words and disambiguation, we know that take is an extremely polysemous word. Okay, there are close to 50 to 60 meanings of take, but take credit is a combination which has a special property. Okay. Here take credit is an example of light verb. Take is a light verb here. Okay. Then taking hostage is also a special combination, and the meanings of take, normal meanings of take, will not help here. Now the point is that why worry about all this? If multiwords is a very small phenomenon in natural language processing, how does it matter? We need not be concerned. But that is not the case really. Multiwords are of the same order of magnitude as the number of single words. This was found out by Jack and Duff in 1977. Okay. And if we look at the WordNet repository, then 41%, about 40% of entities in the WordNet are multiwords, word combinations. Okay. So we have to take them very seriously because their numbers are high.
Do we know if this is something that is has a lot of variability across languages? This kind of statistics?
This is almost universal. This is almost universal. All languages have this kind of proportion, multiwords and single words. Then multiwords have their manifestation at the lexical level, morphology and syntactic level, semantic level, pragmatic level. So in lexicography, for example, in short, ad hoc, they have to be specially treated. They do not change their form. There can be syntactic and morphological changes, put on weight, put the sweater on. We can change the structure, we can take the constituent words apart from each other. This has a non-compositional meaning. Spill the beans means to let out the secret. Okay. None of the constituent words can be used to get that special meaning. Okay.
Actually, you should not speak about words because that is not defined.
Ah.
Polylexical expression is better.
Okay.
In German, for instance, it has no meaning to say multi-word expressions. One word.
Yeah.
Standexemes.
Yeah. Yeah.
So
Yeah.
term word should be avoided. We should use polylexical expression.
Yeah.
Whether
Yeah,
they are
that's right.
pieces or not is something different.
Yeah, but I think this is what has become fashionable in the field.
It's fashionable, but it's just uninformed.
Yes,
It's
yes.
simply wrong.
I agree. Yes. So there are
Simply because English is so simple with respect to other languages.
Absolutely.
Like Tamil
Yeah.
or German.
Or Hungarian,
Russian.
Russian. So there are polylexical expressions, multiwords, and compounds, and it is important to use the correct expression. I agree with that. Then there are pragmatic level. Kick the bucket filled with water. So kick the bucket can be ambiguous from the context. Now let's see the difficulties. How to handle these problems? Okay, variation in flexibility. A green paper is a paper which is green. A red herring, a herring which is red, is wrong. The night is young, but you cannot say the young night. The structure is frozen there. Okay? The young night is not the correct expression syntactically. I handed in the paper, I handed the paper in is okay. Kim ran over the dog, Kim ran the dog over. This expression is doubtful in terms of idiomaticity. Okay? So some expressions can be taken liberty with in terms of syntactic flexibility. Some expressions cannot be. The night is young, you cannot say young is the young night. By and large has its does it have an internal structure? Preposition, conjunction, adjective. Okay. So does it need this kind of syntactic processing internally or no? More difficulties. Sometimes the multiwords can be very long. Length. Language learning system design. So design of system for learning of language, and we have to get the relationships amongst constituents. A language evolution, that brings in new multiwords. So cell phone is a new multiword. Ringtone, new multiword coming from technology. There are regional variations. take away is Australian English, take out is American English, okay, meaning the same thing. So, the influence of language is important. Then there are complex verbs, which is a phenomenon of Indian languages. To yawn is Jumhai Lena, okay, to yawn, and this is a verb and noun combination. This noun is not the argument of this verb, but it's what is called an incorporated noun. Okay. Then there are these compound verbs, Indian languages, where we have the second verb coming as an semantic addition or an intensifier. So, in Girparna, the meaning is fall down, which is little more emphasized or more intensified than just to fall. So, the Indian language equivalent of phrasal verbs is two verb combination. So, there is this classic paper by Sag from 2002 called Multiwords, a pain in the neck, where the multiwords are divided into different categories. Okay. So, there can be institutionalized phrases. Nowadays, there is a different term for this kind of entities. These are called collocations, strong collocations. And then there is this lexicalization of the form fixed, semi-fixed, and syntactically flexible. In syntactically flexible, there are light verbs, there are decomposable idioms, verb particle construction. Semi-fixed, there are proper nouns, compound nominals, non-decomposable names, and so on and so forth. Okay. So, this has been a classic piece of work which all multi-word entity algorithms have to recognize.
So
yeah.
where do you put idioms in these three?
Idioms will come under institutionalized phrases.
Yeah, they miss a very important class,
Yeah.
namely adjective or definitely phrase and noun. Like you say heavy smoker,
Yeah.
but in French you say gros fumeur, and in German you say a strong smoker, starker Raucher. So all the values of lexicosemantic functions. Here, this is a very important class. You have 20,000 in typical dictionary
Yeah.
of, say, Portuguese, French, for instance. So Milchuk's categorization is far better than this one, I think, because they miss large classes.
Yeah.
In the dictionaries you find about noun, adjective, etc., about half of them, and the other half is support verbs, very often. And quite lower amount of, as you said, institutionalized phrases or arbitrary
Right.
collocations, not expressing lexicosemantic functions.
Yeah. So, this is a little more elaborate slide with examples. So, I think a very important point about multiwords is non-compositionality. Okay. So, yeah, these are different examples, but this is from the paper Compositional Multiword Expressions. These are noun sequence. Is the slide visible, by the way, from the back? Some light here. Better. Yeah. So, there are 9 noun sequences which are still not visible. Okay. So, rat race, palm reading, king snake, these are multiwords. We can make out the meaning of the combination from the meaning of the constituents. Whereas this series is non-compositional, like lip service, motor pool, etc., etc. And the paper also records the number of such entities in the corpora. Okay. Similarly, there are adjective noun sequences which are compositional and non-compositional adjective noun sequences. Now, I think we should spend a little time on these patterns of French adverbials. French adverbials, I think, have always proved to be a difficult proposition for French NLP. That's what the literature says. And we cannot deal with each constituent separately, but in combination. And they are also pretty fixed in their structure. But it is possible to capture them through regular expressions to an extent.
Yeah, we put them in our systems in fixed idiom dictionaries.
That's all. Yeah. And can you put any text between them inside? Never?
No, you are totally right.
Never possible. Never. Yeah. So we simply have to memorize them, put them in the dictionary. And a statistical machine translation system, I think, becomes pretty successful in capturing them in a phrase table with high probability.
Well, some of them
Yeah.
are in two parts, like non seulement, mais encore, tac, tac, etc. In English, not only, but also.
Yeah.
So, but they still can be captured in regular expression.
Yeah. Yeah. So regular expressions have played a very important role, and we can see that these things require part of speech tagging first, and then application of regular expressions. So we go a bit deeper into multi-word expressions, or as you say, polylexical items. In recent literature, we find that the works typically follow this line of thinking.
No, that's a problem.
Yeah.
Because this should be expressed in the terms of the language, that is spoken language. This has no meaning for writing systems without spaces.
Yeah.
Like Chinese,
Thai,
the
for instance.
largest
Yeah.
language in the world is Chinese,
Yes.
no spaces. Japanese, Korean,
Yeah.
Vietnamese, Thai, Lao, Khmer, etc. No spaces.
Right.
So the definition does not apply.
No, one sec.
See.
So there is a the-
And in German, it's different if you have the word. You have many examples where you have a space or no space, and meaning is very different.
even in Sanskrit, yes. So what the field does is that it distinguishes between multiwords and compounds. Okay, so
I mean, it basically have a
Right.
long linguistic analysis.
possible.
We
So-
find that
Yeah.
the thesis by Carlos Ramish.
Mm-hmm.
When we digged into that, we found that
Right,
it
right.
simply is
Yeah.
wrong about the basic assumptions
Right.
and
So-
definitions.
So I agree with you. But point is that multi-words are looked upon as word sequences separated by space. Space is needed in case of multi-words, not compounds.
No,
Not compounds.
if
Okay.
there are no spaces in writing system,
Hmm.
that does
Yeah,
not
yeah.
apply.
Yeah.
And for the largest languages of the world.
Yeah.
So it's simply something like American linguistics where they have observed only English.
Yeah.
So for English, okay.
No, it
Other
also.
languages, no.
Yeah, this also works, I think, for a number of Indo-European languages. You know, like in Hindi is
Writing
okay.
System, if you take Latin, for instance,
Mm.
it had no spaces at some point. After we put spaces in it.
Yeah.
Okay. So why should this be different? No. Analysis should be in terms of what the language is, and the language is spoken.
Mm.
Okay. And writing systems are something different.
Yeah, but you have to do something about it. Okay, so you have to process the language to as much as you can. So this has been a convenience, I would say, which the field has adopted. You know, many of these things are conveniences, and point is they have delivered a little bit. I mean, part of speech tagging we also know is a very deep linguistic problem, and there are assumptions like emission probability, transition probability, which the linguists have laughed at most of the time. But the point is that, you know, part of speech tagging of that kind has delivered high accuracy systems, Okay. And after that, it has been possible to build other layers of natural language processing, which would not have been possible without part of speech tagging. Okay. So, this is a convenience, I agree, and it is probably an engineering assumption, but it has given some result. So, our goal is to look at some of those results.
If you say Indo-European and the tag is only adjective,
Yeah.
it is wrong. The tag should be a compound tag with adjective and short form. So Indo, Franco, German, etc., Anglo-European, you should have 5 lexical units, and part of speech should reflect that and not simply show this to be only an adjective. Right?
Yeah. So,
it should be decomposed into parts with their own tags.
So there is this Euclid part of speech tag set, which is extremely elaborate hierarchical part of speech tag set. But the point is that, why is it that with this 40 or 50 tags have been found to be effective for most of natural language processing? I don't know about French natural language processing.
It's absolutely false. If you take gross grammar, for instance, all the work in Paris, you have about more between 100 and 200 tags, not only 40. And of course, you get high accuracy if you have one tag. You get 100% accuracy under all conditions.
Yeah, yeah.
Okay,
But it's not useful. It's not useful.
So no, that is not true.
No, one tag is not useful, right?
Okay, 40 is not enough.
Yeah.
You have to have a hierarchy. Usually, combinations are between 100 and 200.
In French?
Yeah, of course. Of
Okay.
course in French. All the work by Gross, lexique, grammaire, and so forth.
Okay. So, okay, let's go ahead with this thought first of all.
For instance, noun. Common noun, proper noun, the names of persons, of etc. For names of persons, first name, name of patronym for Russian, and family name, etc. And there are subclasses, and they exhibit different morphological behavior and distributional behavior.
Yeah. So I'm aware of this work on hierarchical pause tagging, but the point is that this has been a very large body of work, and there are pros and cons. Okay, so let's just go ahead with some of these ideas which have been seen in the field now. So, this is an example from Marathi, Sarkar Hakka Bakka Jhale. So this particular combination Hakka Bakka, okay, these are joined together. So the field does not call it a multiword; it calls it compound. Okay, then the meaning is that government was surprised, and this is an example of multiword. This is Garib Nawaz, which means one who nourishes the poor. This should be called a multiword because there is a gap here. So necessary condition for multiwords is that there has to be a space. For the languages which do not use space in their writing system, we have to deal with compounding and segmentation. Okay, that's a different problem. Sufficiency condition. The first condition is that the meaning can be non-compositional. If the meaning is non-compositional, this is a sufficient condition for multiwordness. This is one condition. Okay. The second condition, so for example, here there is an example from Konkani. It means to feel jealous, but literally this means to bite in the stomach. Pota chapta means to bite in the stomach. Okay. All languages have this kind of combinations with non-compositional meaning. So this is from Telugu, an idle person. The literal meaning is a lawyer which sits under the tree for the whole day and doesn't get business. Okay. And then this is from Bengali, means a simple person. The literal meaning is a man close to the earth, son of the soil. Okay. So the non-compositionality is a sufficient condition. Now, if we think for 2 minutes, how can we detect non-compositional multiwords? No amount of rule governed system will be able to do this job. This has to be machine learning based statistical. It just has to be memorized from the corpus, and we need good statistical techniques for doing this. Another sufficiency condition is fixity of expressions. Okay. So in Hindi we have an expression gali dena, okay, which means literally it means to give bad words. Okay, that means to rebuke, to abuse. Okay. And the expression is extremely fixed. You cannot replace these two words by their synonyms. That's not allowed. And this behavior is seen in most of the languages of the world. In English, you have the word life imprisonment, again a fixed expression. You cannot introduce lifelong imprisonment. That's not idiomatic. Okay. So again, fixity of expression is important, and that has to be detected by machine learning methods. Feature extraction, machine learning, that is the way to go. Is there any reason why you cannot put a long here? You cannot explain this. Why not lifelong imprisonment, even though they mean the same thing? We have to say life imprisonment. So this is an idiosyncratic behavior of the language, which can be captured only by memorization.
And we have to say lifelong achievement.
Yes, and we say
Not
lifelong
life
achievement, not life achievement. Yes. So there are many examples of sufficient condition of structure and order. So therefore, we need some natural language processing before multi-word detection. Chunking, for example, is an important step. So the chunker, which is a shallow parsing stage, it identifies non-recursive noun phrases, so noun chunks, and also verb groups. Okay. So natural relationship between multi-word expressions and noun chunks and verb groups is implied. The chunker, of course, is very, very useful for multi-word expression detection. And there are many examples from many different languages. In English, we have an expression most favored nation. So this whole expression most favored nation should be shallow parsed and grouped together after part of speech tagging. Now, the characterization of multi-word expressions, again for languages which make use of space in their writing system, there can be reduplicated words, incorporation of foreign words, handling fixity of expressions, handling terminology, multi-word named entities, capturing noun-noun relationships, and then complex verbs. All these are extremely large activities which are understood in recent natural language processing tasks applying statistical techniques. Okay. Many of these things require simple memorization from the corpus. Okay. So reduplication in Tamil, for example, you can have vittukku vittu, which means in each house. And I mentioned in the beginning that many of the multi-word expressions sometimes require morphology processing at the deeper level. So here there is a suffix which is attached to the first constituent of the multi-word. Complex verbs, of course, is a problem in whole of Indian language scenario. There are conjunct verbs where we have a verbalizer of a noun, and there is an incorporated noun in the whole complex structure. Okay. Maybe I do not spend too much time on this, but I would like to show you this particular slide, which actually captures the computation of multi-word expressions. We divide the whole scenario into a matrix. There are rule-based approaches and statistical approaches. So the rows are on techniques, the columns are on resources. Okay? Techniques and resources. If we have this multi-word phenomenon, which is reduplication based, like things like tick tick, chum chum, which are onomatopoeic. Okay, these combinations capture sounds. Here we can process the multi-word making use of rules and string and morphological processing. These kind of multi-words are easy to process. We don't need any statistical techniques. Rules and string and morphology processing will do.
But for both, you have to add dictionary.
Yeah.
Both of them.
Yes, yes.
Because you don't need any rule if you have it in the dictionary and they are fixed, right?
No, but these things are not stored in the dictionary. The constituents are not stored in the dictionary.
For many of them, they are for multiwords.
Yeah, the constituents in this are not stored in onomatopoeic.
No, I mean
This one, this particular.
To have multiword computation,
Yeah.
you have to take care of compound prepositions.
Yeah, I'm coming to all that.
And they are to be put here. The resources are rules and dictionaries, and in the other part, statistics and dictionaries.
Yeah, I'm coming to each cell actually. Yeah. So then there is reduplication of non-onomatopoeic kind. So like ghar ghar means in each house. Okay. Here we need part of speech tagging and detect that they are contiguous and have same part of speech and same words. This requires part of speech tagging plus wordnet. So for example, Raat Din, day and night, Dhan Daulat, which means wealth, lot of wealth. These are synonymous words. They require both part of speech tagging and wordnet. Then there are these kind of combinations which are non-contiguous and they require parsing. Okay. When you come to statistical techniques, then collocation or fixed expressions like many thanks, we cannot say several thanks. Okay. Many thanks, we can't say several thanks, we can't say much thanks. This is very fixed. Okay. And there is no reason why we can't say several thanks. There is no reason really. So we have to memorize this, therefore it falls into statistical technique. It requires part of speech tagging, okay, and many statistical measures which I will show. Then conjunct verbs and compound verbs, that is a complex verbal structure. This requires a part of speech tagger and a list lookup. For statistical techniques also there are non-contiguous complex predicates which require parsing. Now of course there is a very important difficulty, which is that parsing comes at the fourth layer of natural language processing. Okay. So there is a circularity in multi-word processing and parsing. Parsing may require multi-word to be detected, and multi-word requires parsing. So this conundrum cannot be resolved. Okay. We have to break this circularity by dictionary access and so on. So we have developed a multi-word extraction engine for multiple Indian languages. I don't think I'll go into the details of that. So here is the block diagram, which takes the corpus, does part of speech tagging, does regular expression filtering, linguistic filtering, semantic filtering, statistical filtering, manual evaluation, and finally we get a list of multiwords. There is a whole pipeline of processes which happens in the multi-word processing engine, and this is typical of any language. Many languages have this particular pipeline for multi-word detection.
Actually, there is MWE toolkit prepared by Carlos Ramirez.
Yes,
Did you use it?
I know about that.
It enables you to work with many different pipelines. There is no one pipeline for each language, but in the field, there are many trials with putting many different things in pipeline, and it gives the possibility to compare them, to implement them, and to run them, and to compare the results of different extraction techniques. Also for evaluation, you can use the same toolkit, MWE toolkit.
Yeah, I know about that. Lahari told me about it.
But the question was whether you did use it or maybe put it in that toolkit to then try with other slightly different modules in the pipeline.
Right. So in that toolkit, we thought this particular phase was not involved. Okay, we have finally put a human being at the end just to inspect the multi-word list. Okay, so I think I should now go into some named entity discussion, but yeah, almost time. So only I want to say that for statistical techniques for multi-words, there are many different statistical measures like normalized PMI, then log likelihood ratio, bidirectional log likelihood ratio, and so on and so forth, which is there in the slide, and they are also of course discussed very well in on the net. Let me go into named entity recognition. So, named entities and the philosophy of language. Proper names are defined by what is called descriptivist theory of names, coming from very old philosophical traditions like Frege, Russell, Ludwig, Wittgenstein, John Searle, and so on and so forth. And there is this causal theory of reference, which is due to Saul Kripke. So, this is a philosophical tradition I will just mention. The problem is defined as follows. If we have a test document, then named entity identification simply marks ones and zeros on the whole text, name or no name. Okay? And the whole thing is a binary classification problem, and we can make use of discriminative models like support vector machines and so on. A more complex problem is named entity recognition. So, given the test document, we have to find the entity and its class. So, named entity recognition is the task that seeks to identify and classify each word or phrase into a predefined category. So, some problems in identifying the named entities. The named entities can have variation. For example, you can have Barack Obama, Obama US President. So, this is a problem of reference resolution. The same name is referring to the identical entity. Named entity types can be ambiguous. 1945, is it a date or time? Okay. Washington, is it the location or a person? May can be person or month, or even it could be a modal verb. Tata, a person or organization. Okay. So, this kind of ambiguity of names arise all the time, which can be resolved only from the context. Severe problem is caused by what is called metonymy, metaphorical usage. Okay. So, person versus artifact, organization versus location, company versus artifact, location versus organization. Many of these ambiguities arise because of metonymy or metaphorical usage. For example, if you look at this sentence here, Washington voted Washington to power. Okay. So, this first Washington is the place Washington, this Washington is the first president of USA, and this Washington is actually metaphorical usage. It means people of Washington, not really the place Washington. So, many times ambiguities arise because of metonymy. So, named entity recognition is also a fairly recent problem, and the task has been standardized by what is called the ACE tag set. ACE is automatic context extraction. This is the standard. It is a hierarchical tag set for names. So, first class of tag sets is NMX. NMX can be person, organization, or location. Okay. Under person, you can have individual or group. Under individual, you can have family name and title. In organization, you can have government, public company, religious, non-government, political, paramilitary, charitable association, etc., etc. So, you can see the level of detail that has been used to standardize the tag set. This is known as the NMX tag set. Then you have what are called NUMAX tag set, which can involve distance, money. Under money, you can have quantity and count. Then you have what is called TIMEX tag set, time, date, and day, and also period. So, the tag set counts at the first level there are 3, in the second level there are 43, third level there are 40, totally there are 86 tags which are organized hierarchically for named entity recognition. Okay. So, there is a hierarchy of tag sets, and it requires complex algorithms to detect them. So, how do we annotate? If you are using NMX tag set, then you can go to any level of depth. NMX refers to names of individual person, also includes names of fictional characters found in stories. The tag structure is person, subtype is individual. So, for example, Abdul Kalam, one of the presidents of India. So, this is of the type person and the subtype is individual. Okay. So, this kind of tagging has to be done on the text. Then 1.1.1.1, this is a deeper level of annotation. This is family name. Okay. So, we can have individuals as subtype, and then subtype 2 is family name. Okay. So, complex annotation is employed for named entity tagging on the text. So, there are different approaches to named entity resolution. One is dictionary lookup, the second is rule based, uses lexical, contextual and morphological information. Maximum entropy theory based, which is statistical. Hidden Markov model based approaches also exist. Then there are conditional random field based and hybrid methods, which are combination of statistical and linguistic. The statistical approach is purely based on features. Named entity recognition is a task which really has to work with features a lot. Okay. And it has been seen that feature based approaches have been, or discriminative approaches have given better results compared to generative approaches. So, here is a summary of the approaches. Named entity recognition can be supervised, unsupervised, semi supervised and hybrid. There are some examples. Under supervised, we have graphical model based CRF, deep learning based, which is neural network, unsupervised methods, which is corpus statistics based or rule induction based, semi supervised NER using what is called ADA boost. This uses a little bit of corpus and then begins to boost the algorithm. Hybrid methods, CL gene has been a well known approach. How do they perform? In graphical model based, it can model sequences. That means it can model, it can deal with multi-word named entities. It can take features, and the best results on the CoNLL 2003 standard data set, which is referred to by most papers, there was an accuracy F score of 84%. If you take the corpus statistics based method, it makes use of inverse document frequency, term frequency based approach. It cannot model sequences. Okay. It can take features, and on a standard corpus for Indian languages, this gave an accuracy of about 68%. Then there is this rule induction based method. It can take features, it learns new rules from the corpus. The best reported result is 87%, and it is not able to model sequences. I am sorry, I do not have time to get into details of why sequences can be modeled or cannot be modeled, but these are mainly approaches. Then semi supervised approaches, ADA boost has been used and reported accuracy is about 80%. CL gene is a method combining both statistical and rule based, reports about 72% accuracy. And finally, there has been currently the approach seems to be based on deep learning and neural networks, and reports pretty high accuracy, very high accuracy of about 90% on this CONLL data set. Okay. So, our last lecture will be on deep learning, and we would like to understand why deep learning is giving surprisingly good results in many cases without much processing, without much pre-processing on the data. Yeah, please. Yeah.
Which is the preferred method? I mean, if you have to split a lot of tokens
Yeah.
in a certain amount of time,
Right.
what should we use?
Right. So, this problem we have faced in India also. So, for example, we have to detect named entities for very large corpus for information retrieval purposes. So, we know that when we create posting lists, that is inverse document indices for search engine, then if some entities are known to be named entities, then the search performance becomes higher. Okay. So, it is important to index entities with their name information, but in an information retrieval scenario, the corpus is extremely large, and how do you detect named entities? Fast and easily. So, we need lightweight methods. There we have found that corpus statistics based methods do well. If you make use of IDF, inverse document frequency, and residual IDF, then these two measures produce good results. Okay, I can, if you write an email to me, I can send you the paper on this. So, historically, Mark conference is the one which recognized that named entity has to be taken very seriously. Very old natural language processing did not think this was a very important problem. And then there were these message understanding conferences which did a pretty elaborate study of names. So, there are many different features which are used for named entity recognition: word, digit, common word ending, function word, patterns, list lookup, and so on. You can look up the slides. The statistical approaches make use of these measures. Okay, IDF is quite frequently used, residual IDF is also used. So, I will just report something on deep learning versus other methods. We recently conducted some experiments on 3 languages, English, Marathi, and Hindi, for only 3 kinds of entities: person, location, and organization. And the 3 algorithms were conditional random field deep learning and MEMM and CLGene. The deep learning method is still not producing very good results. You can see, the results are very good for conditional random field. Conditional random field has proven to be extremely effective for named entity recognition, but the problem is that for very large corpus we have prohibitive training time. Conditional random fields take enormous amount of time to train. Okay. On the other hand, deep learning, once you have got the neural networks, are quite fast. Okay. So, this is some study which we have undertaken now, and we are able to create named entity clusters using deep learning. So, here there are references for named entity recognition, important references for multiwords. Okay, thank you. So, there is a bit of a change in the sequence of lectures.
I will announce.
Oh, you will announce it.
I will announce it because I have to send. Also, lecture 3, the video will be ready today only because they have to encode in MP4.
Okay.
So it will be on the website. Please give me all the address. I will complete the list later in the day and send the same. We call again.